Alright. Good evening, everyone. Welcome to stream. Just comment if there are any problems with audio and video because these are not working properly sometimes. Alright. So we are back again. I don't know, this is sixth live or something. Taking a break after an hour is very important. That is something that I have understood, and I don't want to cut the stream every time. So instead, I will just take the break every hour. I'll just turn off the audio and I will take break and I will come back again. That's it. It should be as simple as that. All right. We are at 2025 set 1, and I guess we were solving the questions very intensely and very happily. So some question regarding the non-abelian group. Yeah, this one we completed that. Theory of computation question. This is 40. Okay, we are here again. Deterministic finite automation. Okay. Define over an alphabet. A, B, identify to the languages that accept the set of strings containing even number of B's. So let's try to track it out. A, B, B, A, B, yeah. Right, if you do some sort of track, what is this? This means it is going to end here. It might end here. So no, this is not correct. The set of strings containing B, A, B. A, B, B, A, B, A, A. Let's track it. So he talked about B, A, B. B, A, B. After that, it might be B, 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 A, B, B, A, B. Set of on strings. Okay. Let's do this. A, B, B, A, B. That ends over there. And A, B, B, A, B, A, 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 B, B, A, B, A, B, B, A, B. No, right? Ending with pattern B, A, B. If it ends with pattern B, A, B, it ends over there. So this is only ending. This is correct. The set of all strings not containing pattern A, B, A. Not containing pattern A, B, A. So what I wanted to say is A, B, B. No, that's false as well. I can only see option C being true. Oh my god. Okay, nobody saw this, but this is like a big goddamn milestone for me. A disk of size. Okay, this is motivation, man. This is motivation. This is the power of consistency. Whatever you might want to write here, just write. We did it. We did a 2 marks theory of computation question, and it is official. It is official. We did a 2 marks TOC question all by our own. Okay, this is very important, especially for my, what do you call it, depressed ass. All right, jokes apart, we have well done, well done, well done. Yeah, you people might not know how big of an achievement this is for me. I mean, there are a lot of people who solved it, but wow. 512 megabytes disk, okay, 64 kilobytes block. A file is stored on the disk using linked relocation. I don't know what that means. We will soon figure out. In linked relocation, each data block reserves the 4 bytes to store the pointer to the next data block. Got it. The link pointer, the link part of the data block, the link part of the last data block contains another pointer, also 4 bytes. Suppose a file of 1 million bytes need to be stored in disk. Assume 1k is equal to 2 power 20, 1m is equal to 2 power 20. The amount of space in bytes that will be wasted due to internal fragmentation is internal fragmentation. Okay. So 4 bytes, all right. What is the size of block? 64 kilobytes. For every 64 kilobytes, 4 bytes will be wasted. And we are talking about 64 into 2 power 10 bytes. And the size of the file is 1 million bytes. So that is 1 into 2 power 20 by 64 into 2 power 10. That is 2 power 10 by, how much is this? 2 power 6. That is 2 power 4. So that is 16. No, what did you calculate? What did I calculate? Okay. So 64 bytes. 64 bytes? No, my bad. 64. Okay, allowed that. Okay, 64 KB. 6, 5, 5. Each data block receives results 4 by. Now, what is this? Okay. We are not supposed to find the internal fragmentation. Alright, I will give myself an intuition of what internal fragmentation is. Let's say this is a disk block and we fill this, we fill this, we fill this, we fill this. and this is only filled until here. So this part, wait, I messed everything up. All right. So it is only filled until this part. Come on, yeah, this part. Internal fragmentation. We need to find how much that is. 61 kilobyte is 1024, and 64 kilobytes is 4 4s are 16, 4 2s are 8, 9, 0, 4 0 9 6, 6 3s are 18, 24, 12, and 14, 0, and that is 1. This is 6. So 6, 9 plus 4, 13, and that is 5, 5, 6, 5, 5, 3, 6. Total 4 bytes pointer. Pointer, right? So 65532 only. And now 2 power 20 by 64 into 2 power 10. Actually, slightly less. Less. So what I'm trying to do is, this is 2 power 20 by, how much is this? 2 power 6 and 2 power 16, that will be 2 power 4, that is 16. So exactly 16. But denominator is slightly smaller than 64 into 2 power 10. So answer is slightly larger than 16. It will cause entire new block. Even if it is 1 byte greater than this, it will cause new block. So it is 17. We got it. But 1 to 16 are completely occupied. Okay. So 65532 into 16 in 16 blocks. That will be 65534 36 minus 4 times 16. That will be how much? This is how much? 2 power 10 and 2 power 6. That is okay. Okay, we don't want to do this. This is total size. Total size of what? 2 power 20, yeah. And how much is completely stored? 16 blocks of 65532. Okay, I just need to get this to integral powers of 2. That's it. This is going to be 2 power 4 and this is going to be, we already did that. 2 power 16 minus, right, it is 65536 minus 4. So 65536 is 2 power 16. We've seen that. Seen that, and this is 2 square. A power m minus a power. There is no formula. Formula is there. Not this one. How do you calculate the 64 effectively? Alright. Now what I meant is okay. Think of it as mod in operation. What I meant is 2 power 20 minus 65532 times 16 is equals to 64. How to do that? Okay. Okay. Okay, dude. So we are supposed to do that 1024 times 1024 so 16 4 2 0 8 190 4096 and 2048 and that is 0 and that is 1024. That is 6 and 8 to the 16 and that is 17 and 415 so 448 401. Okay, my guy told like shut up and do it. 65532 times 16 so it is 6 2s are 12, 6 3s are 18, 119, 6 5s are 30, 131, 6 5s are 33, 33, 6 6 are 36, and 3 is 39. And 2, 3, 5, 5, and 6. 2, 9, and 2 is 11, 3, 4, 5, 5, 3 is 8, 9, 5 is 14, 6, 4 is 10. So you got 1048512. So if you subtract these things, what will you get? This is 4 and this is 6. Everything else gets cancelled out. So that is 64 remaining. 64. So 17th block is only 64. But what is the entire size of 17th block? 64 kilobytes. That is 6. 5, 5, 3, 6 minus 64. If you do that, that is going to be 2. And 13 minus 6, that is 4 plus 3 is 7. That is 4, 5, 6, 5, 4, 7, 2. Is that the answer? No, what? 6, 5, 5. 6, 5, 5, 3, 2, right? Wait. Wait. 6, 5, 5, 3, 2 is available. Data. When calculating internal fragmentation, you only take 6, 5, 5, 3, 2, not 6, 5, 5, 3, 6, right? Because 4 bytes is our linked list. The actual data capacity. You need to check the actual data capacity. Check actual data capacity. So 65532 minus 64, that gives you the answer. 12 minus 4, that is 8, and 13 minus 6, that is 7, 4, 5, 6, 6, 5, 4, 7, 8, 6, 6, 5, 4, 8, 13. You motherfucker. Oh god. 12 minus 4. 12 minus 4, that's 12 minus 6. That is 6 and 4. 6. Oh god. Do the subtractions, dude. Learn the subtractions. Okay. Thank god nobody saw that. Question 41 we completed. And now to the question 42. 3 address code sequence. The code sequence is split into basic blocks. The number of basic blocks is... Okay, what am I supposed to find out here? What am I supposed to find over here? Compilers and start and end nodes in building C. Basic blocks and nodes. Let's see. We need a bit of theory. Okay, it is compiler design. Basic block is a sequence of consecutive statements in which control enters at the beginning and leaves only at end without any branching or halting except at the end. Identify leader, first statement. End of a program. First statement of a program is a leader. Target of go-to is a leader. Group of a leader. Alright, I need to know some basics of compilers. A compiler is a program that translates mission code, lexical analysis, tokenization, syntax analysis, parsing, semantic analysis, intermediate code generation. In the intermediate code generation, 3 address codes comes in. Improves efficiency, code generation, code linking and loading. Final executable is prepared. TS is linear row-level representation of the code. Each instruction has almost 3 operands. Has at most 3 operands. three operands. Got it. Operands can be variables, constants. Go to X is result, operand, operator. T1 is equals to C plus D. T2 is equals to B plus T1. Temporary introduced by the compiler. Got it. Mission independent. Scratch bad notes. Makes sense, makes sense. Makes sense. Learn intermediate code generation. They are not basic blocks, okay? They are helper nodes for analysis. Basic block is a sequence of consecutive statements in which the beginning and leaves only at the end. Or halting except at the end. Later. Okay. So the code sequence was written. That's good. Inner loop 1003 to 1009. Okay. Okay. A blazing bulb is a straight line. Okay. Design. So first statement, target of port at 1009. Okay. First statement is a leader, and once you came over here, you will find out that target. Okay, this is the second block, and 1010 target. Okay, got it. The statement immediately after go to is a leader. And again, this goes to the go to statement. This is also a leader. Good. And 1012 is also a leader. So 1013. All right, we will make an analysis of this one over here. So leader, and we read this one. So it will go to 103 1. This is 2. It will iterate over 10 times, and this it will go to where 1002. That is 3. Wait. This is 3 because next after go to, this is 5. Next after go to, and now it will go to 1013 6. Go to pointing to this one 6. We got it. My god. A computer has a memory hierarchy consisting of two levels, cache, L1 and L2, and the main memory. The processor needs to access data from memory. It will first look in L1 cache, that's correct. It will go to L2 cache, and then it goes to main memory. Data is definitely available. Its return access time of various memory units is shown in the figure. The average memory access time of nanoseconds. We should be able to make this one. This is easy. Yeah, alright. AMAT, average memory access time, is equals to hit rate no, there is a formula. What is the formula for average memory access time? Hit rate times hit reward minus time taken to access the memory when there is a hit. Okay, hit rate hit plus miss rate into miss penalty. Hit plus miss rate into miss penalty. You are supposed to add all of those. Should you add like that? Alright, what is hit? Time taken to access the memory when there is a hit. Okay, got it. So I don't know about the L1 cache. Hit rate is 95%. Okay, it will be access time. Hit rate is 90. So you need the access time of 10 nanoseconds. Okay, I need to look at this one. So I think this is hierarchical access. We just need to find local access time. Okay, time one is 10. T2 is equals to 10. Okay, T3 200 minus 20, that is 180. Okay, hit rate is 0.95. Hit 2 is 0.85. So hierarchical formula 11.85. No, what the heck is this? Okay. Get 2025 Saturn key. Question number 433. I don't know. 11.83 to 11.87. Okay. Am I supposed to read all of this one? So, what did this guy do? H1, L1 cache hit rate, L2 cache hit rate, L1 total access time, L2 cache access time including L1 cache miss penalty. So if we apply this formula, Even the today one, okay. Okay, look at the analysis, man. Guess I need to look at the question from the question itself. Can we control F in this one? Computer has memory. Alright. The control F. Including L1 cache miss penalty, 20 nanoseconds. L1 times L1. L1 miss rate. L2 hit rate. How to push this one? Like, how to push this one? I have no idea. Zero 0.95. Okay. 10 into 10 plus 0. Well, I say there is some. I don't know what my guy is on to. All right. Okay, that's a big one. Why going into controversy now? We don't even know the normal questions yet. But reading the controversial arguments is still better than reading other meme internet arguments, right? So we are back. Yeah, this is average memory access time. So cache L1 hit plus. Okay. Now what is the hierarchical cascade problem? T1, that is T1 plus 1 minus H1, that is miss rate times miss penalty. T2 is miss penalty plus 1 minus H1, alright, times 1 minus H2 into T3. Alright, so here 10 plus 1 minus H1. So only if it, it comes to L2 only if L1's missed. So 0.05, what is the value of T2? Twenty nanoseconds. Okay, there is 0.05 probability. Here it takes and 0.05 into 0.15 into no into 200. If you solve this, that is 10 plus 0.1, it will be 20 times 5 is 100. 1 plus 0. Alright, this is 15 5 are 75, and this is 2 dots, and that is 2 dots. 1, 2, 3, and 4. 0.0075 into 200. So that will be 75. 0.75 into 2. That will be 1.50. That will be 12.5. No, what? Uh-huh. That is what we done, right? Okay, only that made sense. Okay, I thought I made this answer. Okay, I mean it is a controversial question and even a report was filed on that, so I don't know. Alright. An optimal pay. Alright, I'm skipping that question. I mean, we have understood the gist of that. In an optimal page replacement algorithm, information about all future page references is available to the operating system. A modification of optimal page replacement algorithm is as follows. The OS current paper index only up to next page. And page at the time of allocating a frame to a page. Process access the pages in the following order of page numbers. The system has 3 memory frames that the number of page faults that will occur during the execution of the processes. I don't know where she is gone. A page fault occurs in a program tries to access a page that is not currently in the physical RAM. Okay, I have read that one before. The OS must then bring the page from disk into RAM. Access time will be slower, minor page faults. Page is in memory but not mapped correctly. So it's a costly one. Virtual memory, logical memory is divided into pages. Memory is divided. When RAM is full and a new page is needed, the OS decides the next question was out. Raised recently was out. Set only by that will not be used. Yeah, good. Fraction of memory access. Lower the page fault rate, better the performance. Set of pages the process. The working set with the RAM. Trashing. Okay. A process accesses pages following order of page numbers. Optimal page replacement up to next core. Let's see. 1, 1, 3, 3, 1, 3, 1. Can you help me some page fault question? Toppers are there. I will simulate the reference string. Okay, let's read this one. Alright. We'll simulate reference string with 3 empty frames. Timur run a replacement as named. Current value was the next radiation. Phase 1. Okay. Frames before. Hmm. 3 frames before empty. Yeah, 3 empty boxes, frames and RAM. If the number is already in the box, not in the box, page only you must put it in. If all boxes are full, you must kick one number out. With 3 frames, no frame. Okay, next 2. Next 4, not there. Frames full, so I picked 1. Depends upon replacement on not found. Okay. Keep on. Okay, now I got it. So, empty frames. Now as products. One, 3, 4. 4 is needed, but it is not there. 2 is needed. first time. Okay, 4 is long, 1 is last needed, so 1 with 4 hit. Three, 1, 4. Okay, kind of understood it now. I need 1, it is not there. Alright, I'm trying to. 4 is not there. So when I found a card, 2, 3, 4. From 3, what do you need? So 1 to 4 is needed. 3 can be replaced with 1 is hit, 2 is hit, 4 is hit. Now 3 is not there. 3, 1, 4. 3 needs to be pushed. You need 1 and 4, so 2 needs to be replaced. 3. Wow. Okay, I understood it, man. Boy. Okay. What's the question number? It is 44. 55 questions we got. Okay, people, we will talk after some time. Bye.